So today we're going to talk about the design of shafts and beams. The difference between shafts and beams being that a shaft is an object that is primarily intended to resist torsion, although it may also experience bending, whereas a beam is an object that's primarily designed to resist bending. So we'll start with coverage of shafts. Like I said, primary objective is to resist torsion, but because of the way these forces are applied, it may also experience bending stress. When we covered shafts in the past, we only considered the design for torsion, but now we're going to go back and consider the full design. So like you see here, we might have some gears acting on a shaft, and there might be some loads applied to those gears, which will certainly cause this torsion. So we have this torsion and that torsion. But the other thing to consider is that those forces can be broken up into their components in the, say, the horizontal, vertical directions, and each of them then is a transverse load. So essentially what we're doing is we're taking that load, that axial load that's acting at the outside of the gear, we're moving it to the center of the shaft, but to do that, you need to apply that moment that it would have on the shaft. So you end up with your force components acting at the center of the shaft as well as the moments. So those moments give you this torque diagram. So you can see that in the middle section, you have a certain amount of torsion. In the ends, assuming these are the same magnitude of torsion, you're going to have no torsion. But we also have bending moment about the X and Z axes. And those are going to be caused by those point loads. So you can see that for the moment about the X, we have two forces that are contributing to this bending moment. We have this vertical force upward and this vertical force downward. And you can see those are causing us to have changes in our moment slope, the slope of our moment diagram at those two locations. What I didn't show you on this slide is the shear diagram. Typically, it'd be easier to start with your shear diagram, and then you can go quickly from your shear to your moment diagram. And then in the other direction, we have just this one horizontal load that's occurring here where we have this change in the slope of our moment. So you have two different moment diagrams depending on which direction the moment is about. In order to design our shaft, we want to find out the net moment, rather than having it broken up into those two directions, especially since our shaft is circular. It makes a lot more sense from a design perspective to figure out the moment about some arbitrary axis that is the resultant of those two components. So you can do that with this equation here, where we take the sum of the squares of the moments and then take the square root. That gives us our resultant moment. That resultant moment will then have a distribution like so. This is your bending stress distribution. It won't necessarily be vertical or horizontal. It's going to be about whatever arbitrary axis becomes your neutral axis. And that distribution is MC over I. If we want to be real particular, we might say negative MC over I. Then you have your shear stress distribution. So that torque gives you this distribution of shear stress where it increases linearly as you go towards the outside radius. And you compute that with TC over J. TC, these are the maximum values because we're using the maximum radius, C. C would be this value here. But if you wanted to know the value at any point in the shaft, you would insert that respective radius. But oftentimes what we're concerned about is the maximum value because we're wondering whether the shaft is going to fail. Here you can see a summary of your stress state. You have the torsion from that applied torque, and then, or sorry, you have the shear stress from the torsion, and then you have the normal stress from the bending. And you can show that as a plane stress state. If you want to design the shaft, typically you'll be designing it for some maximum allowable shear stress that will be a function of your material that you're using. If you think back to Moore's circle, normal shear, you have some Moore's circle, and you have a stress state on here. This might be your given stress state. Let's draw this a little bit differently. Okay. This might be our given stress state. So in order to get that radius, we can do Pythagorean theorem, where this here is our shear stress that we're given, this vertical distance to that stress state. And then this horizontal distance is going to be your stress over 2 if the opposite, my circle's still not drawn properly. If the opposite side of that circle, it has a value of 0. So my circle, if you'll allow me, I'm going to keep revising my circle. I want this opposite side to be here. Okay, so that's terrible circle. But the point is that in our given stress state, we have stress in one direction and not the other direction. So what we're saying is that when we divide that by 2, we're getting this horizontal leg. So we're calculating this hypotenuse, which is going to be the stress over 2 squared plus the shear stress squared. We can plug in the values for normal stress and shear stress. So MC over I, TC over J. But for a circular solid section, mind you, I said solid, J is equal to 2I. You can get a similar relationship for an open cylinder, for a hollow cylinder, but this one is in particular for a solid shaft. So J is pi c to the 4th over 2, which happens to be 2 times the I value. So we can plug that in. We can replace this 2I with J, which means that we can pull out the C over J term. And we're left with square root of moment squared plus torque squared. C and J are both geometric properties. So if we're trying to design the geometry of the shaft, it's much easier if we only have one geometric property to target. So fortunately, J is a function of C. So we can plug that in, and now this part outside the radical reduces to 2 over pi c cubed. And now we have a relationship between the allowable shear stress and this right-hand side, which is a function of only loading and radius. We typically know the amount of loading we're trying to withstand, and then we can back calculate our radius that we need. So the equation to calculate your required radius for a solid shaft is going to be 2 over pi over the allowable shear stress multiplied by square root of the moment squared plus the torsion squared, and then that whole thing cube rooted. And that'll give you a value for your solid shaft radius. You could do the same thing for a hollow shaft. You just need to express I and J in terms of C, and you'll be able to calculate the equation. Questions? I'll give you just a second to get this written down. Yep.
So if you have multiple moments and multiple torques upon an object, is that a square root between the sum of the moments and torques?
Good question. Not necessarily.
Okay.
So these moments and torques are probably acting at different locations. So when you're doing this calculation, it pertains to a particular location.
Okay.
And so if we go back, you'll notice here that your maximum torsion is in this central region. And your maximum moment in one case is over here on the left, which actually is this location. And then your other maximum moment is that location. So as the engineer, you've got to kind of figure out, where do I expect the worst behavior? Or maybe you just check them all. For instance, it might be this cross-section 1, it might be cross-section 2, or there might be some region in this area where actually the combination of the two moments gives you the worst case scenario. And actually for this one, that's probably going to be fairly easy to get because you can get that that resultant moment and then figure out where that occurs. But the problem is if you just take this maximum moment and that maximum moment and get the resultant of that, you're not looking at a particular location. You're taking two maximum values and getting an even bigger maximum, so you're being conservative. But a lot of times in design, we can't be too, money is always one of the factors that we're looking at. So being overly conservative doesn't always help, or it doesn't always make the best design. So you might need to give some more thought to optimizing and figuring out exactly where your worst case happens.
Yeah.
And yes.
So like on a stoplight, you notice like the shaft, it gets smaller as it gets longer. So designed for that.
Right, because you're looking at that changing moment as you go along, and as you get closer to that free end. He's talking about a stoplight where you have the big arm hanging over with the lights, signals. You have less moment occurring at the end. So they're optimizing the cost efficiency of that by saying at this end where we have smaller moment, we can have a tapered, smaller cross section. And interesting, a lot of times in engineering, we just say, oh, it's conservative. I'm going to be a little bit lazy in my calculations, and I'm just going to do it in the name of conservatism, which in most cases is fine, but there are some cases where that's actually not fine and will make your design more dangerous. So for a couple examples, one in structural engineering with welding, you might say, oh, I'll just add a little extra weld to this, and that'll make it stronger. Not necessarily the case. The way that welding works is that the more weld material you add, the more vulnerable that weld is to fracture. You have a bigger weld, it's more vulnerable to fracture. It might actually be weaker than if you had a smaller weld. So you only want to use as much weld material as is absolutely necessary. Another example is in mechanical engineering. So I was talking to Maziar Gazinjan, and he was explaining that when you have something that's going to crash and you want to have absorb that impact loading, the question is let me see if I can explain it. How strong should you make it? And you say, well, let's just make it stronger than it needs to be, and that way we're guaranteed that we'll stop whatever impact loading is coming. Well, we'll be able to absorb, we have some factor of safety, and so we'll be able to absorb even more energy than we're expecting. Well, problem is, if you make it capable of absorbing that much more energy, what would happen is things would run into it, and then they would, instead of absorbing, they would ricochet up and over and end up causing a worse collision because it was too rigid now. So he was saying there is no factor of safety when it comes to absorbing energy. You want it to be right on. So depends what you're doing. So the second topic is beam design. In beam design, we're designing the cross-section to withstand the shear stress and the bending stress, which is really just a normal stress due to bending. So at any particular point in the beam, you're going to have some distribution of stress. You'll have this longitudinal stress, sigma x. You have the shear stress we talked about, tau xy. And you, in theory, also have this vertical stress, sigma y, that is going to have a larger value right at the point of application. We often just completely neglect that, but where you place that load, you will have some stress acting in that beam. But it typically is far less than the longitudinal stress that we're designing for. Okay, so as you know, this is the distribution of your shear stress. In a rectangular beam, we have this parabolic distribution. And this triangular distribution is our normal stress, where you have tension on one side, compression on the other side, varying linearly. You have a 0 value at your neutral axis. If we look at the principal stresses, well, let's not jump straight to the principal stresses. If we look at our stress components at 5 different locations on this beam, at the top and bottom, you have only the normal stress, correct? Your shear stress is 0. At the middle, you have only your shear stress. And then in between, you have this combination of shear and normal stress. You can then calculate your principal stresses. So for the top and bottom, those principal stresses are already known. That's just your normal stress. At the middle, your principal stresses are going to be rotated at a 45-degree angle. And then in between, you have some lesser rotation. So when we design our beams, we calculate the maximum stress at the top and the bottom. Because those are the maximum principal stress that's going to occur anywhere in the beam, that's why we directly use that for our design. I mean, in theory, what you need to know is what is the principal stresses and the absolute maximum shear stresses in this object, and that's what you should be designing for. But you can already see from this that those normal stresses are the principal stresses that are the maximum anywhere in the beam. All right, and same thing with the shear. If you take that shear at the middle section, those are going to be your maximum shear stresses. So this equation here is what you're familiar with. Stress is MC over I, or My over I. C and Y are somewhat interchangeable. C being the maximum. Once again, it's hard to design a cross-section if you have 2 different geometric properties you're trying to pinpoint. So I and C, we've combined them into one variable to help with this. So we will say that S, which is our section modulus. So our section modulus is I over C. Then we can solve for S as being equal to the maximum moment over, if you're directly solving this equation, it'd be maximum moment over maximum stress. But you're going to say that your maximum stress cannot exceed some allowable value of stress, which might have some factor of safety built into it. So then you say you need a section modulus that is at least as large as the maximum moment you expect divided by the allowable stress you can have. This is how you design for strength. You also are going to have deflection limits as well. So all of our codes for structural engineering have amounts of deflection that a member is allowed to experience. And so you could go through the same procedure where essentially you need to pick an appropriate I value so that that equation for deflection will not exceed what's allowable. In order to do this, the first step of your procedure is always going to be to get your maximum shear and moment. So you're going to do your shear diagram, your moment diagram. Then you're going to check for the required S, and you're going to choose one that's slightly larger than what's required. From that, you can determine your cross-section. If it is a geometric cross-section, like a rectangle or some other geometry that you can calculate the I for easily, then from S, you can figure out what I over C, what the exact values of I and C need to be. Or if you're dealing with, say, a steel shape, there are tabulated values for S, which actually that's true of rectangular wood shapes as well. But there are tabulated values for all the steel shapes that tell you directly what the S value is. And then you can pick, typically you pick the one that has the lightest weight. So once you know that it has a sufficient strength, you then want to pick the lightest weight because weight equals money. As I've said before, for beams, we're generally designing them for moment and then checking them for shear. So if you want, so that would be the procedure I would do. I'd pick my S based on the moment over the normal stress. Then with that S, I'd come in and I would check that this equation is satisfied, that I have sufficient shear strength using VQ over IT. And remember that you can simplify that for a rectangular cross-section to 1.5 times V max over A. Or for a wide flange beam, it's just the maximum shear divided by the area of the web. Then if you have connectors, you need to give some consideration to those. This should be your allowable Q, little q, so your allowable shear flow needs to be greater than VQ over I. Any questions?
You want to put greater than or less than?
Your allowable value should be greater than your demand.
Oh, right.
All right, so because this is nothing new, it's just simply solving for the cross-sectional dimensions and using equations you're already familiar with. Instead of going through an example, I have 2 in-class assignments for you. Given that Vanessa is going to come in here in probably about 15 minutes, I don't think you'll have enough time to get through both of them. But if you can kind of pick the one you're more interested in, or maybe work individually, then compare your solution with another student. And let me just verbalize what these questions are saying. So in this first example, we have a beam. You can assume these are pins or rollers at these 2 supports. And we have an allowable normal stress, allowable shear stress. And I'm saying that the height over width should equal 1.25. So if this is your height and this is your width, and you take the division of those 2 numbers, I want that to equal 1.25. You need some kind of a guideline like that. Otherwise, there'd be an infinite number of solutions that you could pick. And then in the second exercise, you have an allowable shear stress. Your inside diameter is 15 millimeters, but you need to determine your outside diameter given the loading that occurs. And the supports for the shaft allow rotation, but they prevent translation, vertical or horizontal.